Welcome to Usability and Human Factors Input and Selection Methods. In this unit, we will be discussing input and selection methods. This unit will focus on how to select an appropriate technology input method given different technology uses, user populations, and contexts. By the end of this unit, learners will be able to provide a rationale as to why input methods are an important consideration in the design process for health technology. Compare and contrast technology input methods. Select appropriate technology input methods given different technology uses, user populations, and contexts. All clinical information systems are only as good as the information entered into them. Input methods are therefore of great importance in assuring accuracy, safety, sufficient speed, and efficiency to be useful and fit of the technology to the work environment. Careful assessment of input methods and matching them to the task, user, and environment are important before deployment. Some methods are light pen, and touchscreen, as we see with palm-top devices, mouse, trackball, voice recognition, and barcodes, which can be used in situations where transactions related to physical objects must be tracked, such as use in medical administration systems. There are special-purpose keyboards and device touchpads. Gestural interfaces are becoming increasingly common in gaming, certain very specific environments such as public restrooms. Haptic, touch sense controls, in which the user may wear a device that provides tactile feedback or approximated tactile feedback, such as making a click sound on key press, are new developments. Most of these interfaces still involve a microprocessor in some way, and often are still used in conjunction with the keyboard. Context is important in selecting input methods. The physical and cognitive attributes of the task and user should be considered. For example, some hospital environments are noisy, must be disinfected frequently, may have illiterate users, and so on. Other tasks may require fine motor control, such as training simulations or games for surgeons or precise device manipulation controls. The most common input device is the keyboard and mouse. Experienced users can achieve very high speeds, up to 150 words per minute, whereas beginners may type at 12 words per minute. The differences in skill level and need for training and practice mean it can be an obstacle to adoption of clinical information systems, or a cause of suboptimal use. In addition, some clinicians may dislike a perceived association with clerical work. Some institutions find that younger clinicians are skilled and are used to using keyboarding, so that dictation and similar input methods are declining. Keyboards are unsuitable for many healthcare contexts that may not have horizontal platforms on which the keyboard could be put, or requires both hands-free, such as hands-on bedside nursing. Thus, paper and pen are still used for much clinical recording, particularly of patient data such as vital signs and nursing records. These are later transferred to other systems, giving a potential for error introduction and duplication of effort. Voice recognition requires specific approved hardware such as desktop PCs or laptops with sufficient RAM and chip speed. Most current models have this. Systems also required microphones that are certified as conforming to the specifications of the software vendor, incorporated into headsets so that the microphone can be precisely positioned near the mouth or in handheld voice recorders. Voice recognition software makes use of machine learning algorithms that store user speech data every time the software is used and detects patterns specific to that user's voice. Thus, the software becomes more accurate with use. Caution must be used in initial evaluation of the accuracy of software packages for this reason, since initial statistics may not reflect later accuracy and speed when trained. There are 4 main commercial speech recognition engines for voice recognition. Initial use requires training by the user, which usually involves reading a passage aloud, until the software has large enough speech sample that it is able to recognize most of the user's speech accurately. This may take from a few to 30 minutes. There are specialized packages designed for medicine and other fields such as law, and specific modules for specialties. Advantages of speech recognition include the fact that it is natural, requires little training aside from training the software, and perhaps specific commands for manipulating the computer interface. It can achieve very rapid input for ordinary users, around 150 words a minute. Workflow can involve handheld recorders with system of upload to an interpretation and transcription service. Turnaround can be in hours or minutes instead of days, and the user can correct the transcript immediately. Operation can be hands-free, as with desktop directional microphone. Conversion from external dictation services to in-house speech recognition is generally smooth. Some studies show that while speech recognition is faster than other methods, interruptions in the work environment can lead to decreased overall efficiency. Voice recognition can be speaker independent, that is, it will recognize almost any voice. These applications generally can only recognize a limited set of commands. An example is the voice recognition used in automated telephone systems where the user is instructed to say reservations to reach the reservations department, billing for billing, and so on. These may be good for specific situations where commands are limited, but hands-free operation is an advantage. Disadvantages of speech recognition include requiring microphones, headsets close to the face. Misinterpretations by software could lead to uncaught errors, and it is difficult to use in noisy environments such as hospital wards. Confidentiality may be compromised. Dictation into highly structured forms is available, but may not suit all situations or clinical information systems. Recognition of accents and unique individual speech patterns may require extra training, though accent-specific regional software has been developed. Zick and Olson compared voice recognition and traditional transcription services for emergency department (ED) charts and found voice recognition to be much faster, a 3.65 minutes turnaround time versus 39.6 minutes for transcription. However, transcription was more accurate, 99.6% versus 98.5%. Technology in this area continues to improve, so testing for decision-making should be done on the basis of the most current versions. Tablets, including very thin, lightweight tablets with limited ports and restricted functionality, are becoming common. While not designed for healthcare, the small form factor and lightweight can be appealing in a healthcare context and are reminiscent of clipboards that people are used to carrying. Depending on the particular configuration, they may meet many of the requirements of a healthcare environment, including connection to wireless internet, Wi-Fi, barcode scanning, biometric authentication, integrated cameras, robust construction, tolerance to dust and cleaning. However, some models may be fragile or easily dropped, and specialized tablets for particular institutions have been developed to meet healthcare needs. Tablets used in healthcare environments must have some degree of resistance to dirt, rugged construction, ability to be disinfected, as well as technical capabilities, high enough speed, long battery life, and perhaps specialized additions such as barcode scanners. This is a photo of a touchscreen incorporated as part of a pharmacy dispensing unit. Pen input is increasingly common, particularly with small tablets and handheld devices. Gestural alphabets turn users' writing into digitized form. This form of input is slower than keyboard input, and so is being replaced in handhelds by virtual pop-up keyboards. Pie menus are commonly found in video games. They are faster and more reliable for selection than linear menus, since they depend on direction rather than distance. Human ability to detect differences in degrees of angle is very acute. When the circular menu slices are large in size and because the pointer is near them, selection is fast. Fitts' law states that the ease of target acquisition is directly proportional to the size of the target and inversely proportional to the distance from the cursor. The most effective pie menus have 3 to 12 items and are easiest to use with 8 or fewer. One reason pie menus can be fast is because, with practice, the user can retain the direction of menu items in muscle memory so that they need not even look at the menu, and the menu need not even have popped up on the screen. Multiple nested items can be selected in rapid sequence. Pie menus are most useful for actions with logical grouping choices with limited number of items. They constitute a self-revealing gestural interface, and because of memory, it can become easy to mark ahead, increasing speed of interaction. The menus can increase the transition from novice to expert, since every use rehearses the action and forms muscle memory, which the item locations are unconsciously memorized. One disadvantage is that outside of games, this type of menu is not often available in software. Marking menus combine the advantages of pie menus and gestures. Contextual menus are very common, particularly in the Windows operating system. They are launched by a specific user interaction, such as a right click of the mouse. Contextual menus offer a set of limited choices pertaining to the current state of the system. Usually, these pertain to an object selected by the mouse action. It is fairly rapid and also requires little memorization of item locations. Some applications may only make options available in some contexts. This can cause problems in letting users know that the options are available or cause confusion. Screen edge interactions may be different than those the object is located in the center of the screen. Yen studied the use of digital pen and paper by nurses. The digital pen and paper consisted of a pen with a camera, which uses the pattern of 0.3 mm dots on special paper to track the pen location and create a digital representation in memory. This information is later transferred to a computer, and dual digital and paper copies are created simultaneously. In Yen's study, initial excitement gave way to nurses using them interchangeably with regular pens. Often, they would just choose whatever was most handy. The digital pens were bulkier than regular pens and could not fit in pockets. Nurses saw the potential of these, but in execution, the system required more development. Gestural interfaces are a new development that can be seen in everyday life, such as the magic wall used in the news in recent elections. Other examples are the Wii or iPhone. In these interfaces, the body may be the only input device. There is a need to discover vocabulary and metaphors for these types of interfaces. Physically oriented actions are easier to coordinate since the mapping is directly spatial, as with Wii Sports applications or pinch to zoom on the iPhone, which involve direct spatial relationships between the user's action and the output response. These interfaces make fuller use of the human body than just the eyes and fingers used in usual keyboard and mouse interactions, and could provide a far greater range of possible types of input. Gestural components for other applications may be less than obvious and more indirect. An example is the clapper interface for turning off lights. The user must somehow be notified that this capability exists. Multi-touch likewise has more than one point of contact between the user's body and the screen, and this must be told to the user. Some gestural interfaces may involve other devices such as gloves, sensors, multiple cameras, LCD arrays used as pinhole cameras, and so on. Output can be of many different forms such as music, video, device movement, or other types of control, or digital manipulation. Examples can be seen by visiting the URL www.kickerstudio.com. Some gestural interfaces can be almost invisible, such as the sensors which detect movement near a sink and turn on the water. commonly found in public restrooms. This context has become a site for use of gestural interfaces because of people's desire not to touch anything and the need for infection control and decreasing waste of water and paper. All gestural interfaces have three parts: a sensor, a comparator, and an actuator, which can consist of a single physical component or multiple components. A sensor detects environmental changes and/or user actions such as a change in pressure, proximity, light, sound, tilt, motion, orientation of the device, or acceleration. The size and sensitivity of the sensor must be suitable for the purpose and context, or it may be irritating or disruptive to users. For example, devices that use fingers to key in data must present buttons suitable to a range of finger sizes and allow smooth operation. Devices that use a clapping sound to turn lights on or off must accommodate a range of sound that is not so sensitive that it picks up noises of daily living. After the sensor detects a stimulus, it passes information about it to the comparator, which is usually a microprocessor. This compares the new information to the previous state or goal and makes decisions about what is to be done. These decisions are passed to the actuator, which receives the decisions from the comparator as a command and implements an action which may be physical, such as a flushing toilet, or digital, such as an iPhone display orientation when the device is tilted. In designing gestural interfaces, it is important to consider the reason for their use and how they would fit the context. We have already given the example of this type of interface being used in public restrooms for infection control. These types of interfaces may be bad for circumstances where rapid or heavy data entry is required. Touchscreen and keyboards are not as efficient as physical keyboards, or where there is visual-only feedback unsuitable when users are visually impaired. Reliance on physical motions may be unsuitable for situations in which the users may have physical limitations, as may be common among patients. The environment may mandate actions such as wearing gloves, which may also make a gestural interface unsuitable. Subtle movements for those with large hands or lack of coordination could also be a problem. It is also important to consider the social context and avoid gestural interfaces in situations where privacy and embarrassment may be issues. Advantages of gestural interfaces include that they involve natural actions, often less cumbersome or visible hardware, have greater flexibility in the types of interfaces and gestures that can be used. For example, since touchscreens do not involve physical buttons, there is great design flexibility in how many buttons can be used, their design, position, colors, and so on. This means more controls can be accommodated in a small space. There are a huge number of possible non-touch screen gestures, increasing flexibility. Subtlety and nuances can be incorporated, as with common hand and facial gestures involved in daily communication. Finally, gestures can be used to incorporate fun, games, play, exploration, and teaching into the interface. Some of the characteristics of good design for gestural interfaces are discoverability, trustworthiness, and responsiveness. Discoverability means whether or not a new user can discover the capabilities of the interface, including the fact that it is an interface responsive to gestures. Sometimes this may have to be conveyed explicitly via an attraction affordance, that is, a sign, diagram, or other means of telling people unfamiliar with it that this has an interface. An example is the New York subway ticket vending machines, which are touchscreens. A large hand and the word touch and start show inexperienced users that this is a touchscreen and how to start interacting. Airline self-ticketing kiosks have similar affordances. Trustworthiness and privacy are other issues. The system must appear legitimate and that it will not cause injury, physical or financial, for example. Responsiveness is another consideration. Feedback to the user who may be using the system for the first or only time. Clear indication of the system state, e.g. notifying the user that a transaction has gone through. The correct level of sensitivity, aesthetically pleasing and clear design are all important in interfaces which address the general public and users who may have to operate the device without any prior knowledge. In addition, it is important to design gestural interfaces that do not make users appear foolish in public or compromise their dignity. Input method selection should be based on consideration of the task, user and environment, keeping in mind that current technologies can progress rapidly, so that outdated studies and statistics should not be used. Users may have a learning curve, which can affect initial comparisons of two different methods, so allowance should be made for training time. In some cases, study of two different methods showed one to be faster than the other initially. Then, with training or experience, the situation was reversed. Speed and accuracy of voice recognition increases with the use of software, so initial measurements can be misleading. Selection of input methods must depend on knowledge about their efficiency. Some of the research on this comes from the field of experimental psychology. Variables measured may include the speed of interaction, taking into account different types of users and their experience and training, the potential and actual common speeds of data entry, accuracy, muscular and cognitive involvement and limitations, long-term, short-term, and muscle memory, and hand-eye coordination. Results can vary from the experimental laboratory to field conditions, so it is also important to test methods in the setting in which they may be used, with typical users. The presence of noise, for example, can affect accuracy and risk of injury. Size, weight, and similar considerations can have consequences for whether an item will be used in practice, despite the presence of sophisticated software or other desirable features. This may be especially true for such clinical roles as bedside nursing, in which carrying large devices is incompatible with other duties. Design of systems requires consideration of many factors. The following are some questions to ask in selecting input methods. Does the method require a device? Is fine motor control required? How much training is required? How much practice is required? How much motor intelligence is required, e.g., typing requires at least weeks of skilled training? Does the user require both hands to operate it? Is furniture surface required, e.g., a table for keyboards? What speed of data entry is required? Is speed an important consideration? How critical would an inaccuracy be? How easily correctable are mistakes? How easily detectable are mistakes? How many others see the product? This can affect error detection. Some more questions. Does the method have characteristics that make it unacceptable to potential users, e.g., perceptions of rudeness or clerical work? Does the input feed into other complex systems, such as a clinical information system or pharmacy order? Is structured data required? Is the method going to be used in an ambulatory manner, e.g., by a clinician walking around? Is disinfection required? To what degree, e.g., ordinary hospital or clinical versus operating room? Will frequent cleaning solvents be required? Does the environment require special provisions and setup, e.g., wall or partition separating equipment to protect it from dirt and noise? Does the required setup create distance from other clinicians, affecting communication patterns? This concludes usability and human factors input and selection methods. In conclusion, input methods are constantly evolving and improving. Standard methods such as the keyboard and mouse will likely persist, but become device dependent, so that they are used on many mobile and other devices. New input methods require research but can open up avenues of control useful in medicine where requirements such as hands-free or non-touch use can be particularly important for user satisfaction, safety, infection control, and so on. Matching the input method to the senses and modalities involved in other parts of the task is most likely to be successful in the long run.